For numbers 15 and 16, starting with 15 here, we're going to go ahead and factor both the numerator and denominator. Denominator here is the only one that factors. Setting the factors equal to 0, we find that we have vertical asymptotes at -5 and 5. If we canceled the factors, those would become the wholes. But we didn't cancel them, so those are vertical asymptotes. They also, the x values of -5 and 5, make the denominator 0, so therefore we have to take those out of the domain. So domain is all real numbers x, such that x can't be equal to those numbers. The x-intercept would be when we let y equal 0, and the only way that the function's value could be 0 is if the numerator is 0, and the numerator is x, so x equals 0. And that takes care of our y-intercept as well, y equals 0. Now the vertical asymptote, we already said that we have x equals 5 and x equals -5. And horizontal or slant asymptote, that's what that means, SA for slant asymptote. I just call it this whole thing an end behavior model, regardless of what it is. But we can see that the denominator has a bigger degree than the numerator, so our horizontal asymptote is y equals 0. If we peeled off the x off top and then the x squared off the bottom, we get 1 over x. If the denominator again has a bigger degree, then we just say y equals 0 because the values of the fraction are getting closer to 0. So we have a horizontal asymptote at x equals 0 or y equals 0. It's okay if the graph of the function crosses the horizontal asymptote, because the horizontal asymptote really tells us the behavior of the graph at the ends of the function. So when x gets really, really big in the positive and negative direction. So we only have one x-intercept. What we'll have to do here to figure out which direction it goes, because we have to approach all the asymptotes. To approach this asymptote here, we have to go through the origin, and let's pick an x value of, let's say, 1. If you pick x to be 1, you get 1 over -24. So -1 over 24. So we're going to get a value like that. And then if you pick -1, you're going to get a negative over a negative, so it's positive. So same thing. So because the graph of the function is above the x-axis to the left of 0, it's going to approach the vertical asymptote. And then to the right of 0, the values are negative until we get to 5. So the graph has to look like that. Meaning, since you know the values are negative here, you have to get from this x-intercept to that asymptote, and you can't go back up here because there are no other x-intercepts, just 0. Now, the multiplicities of the factors x plus 5 and x minus 5 are both odd, which means you can't have the graph going down. So let me just explain here. The graph can't be down here, because then you'd have the graph of the function approaching this vertical asymptote on both sides in the same direction. You can't have it here because the multiplicity of x minus 5 is only a 1. So therefore, we have to go up here. So the graph has to be up there like that. Okay. Likewise, the multiplicity of the factor x plus 5 that generated our vertical asymptote x equals -5 is also odd. So we can't have the graph going up here. So notice that we have to get from one asymptote to the other. So to get from the horizontal asymptote, when x gets big in the negative direction, to the vertical asymptote here at -5, we'd either have to be up here or we'd have to be down here. We can't cross the x-axis because we only have one x-intercept. So we can't go up there because, again, the multiplicity is odd of the factor x plus 5 in the denominator. So therefore, the graph has to look like that. There you go. No holes in the graph because we didn't cancel any factors. And let's see if we can figure out what the graph of number 16 looks like. I'll do that in the next video.